So let me start with something what is called turnstile stream. Okay. So imagine that yourself that you're trying to maintain some n length vector a1, a2, dot 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 an. Okay, but you don't see this. Okay, what you are seeing is streams are coming where it says update or say jth index add minus a or ith index add plus 37, something like this. Okay, so I know that there are n size index, and every time it is coming, all I'm trying to know is that, like, okay, at ith index I go and add something. Okay, at jth index I go and subtract something. So it could be both. So in some sense, it is this is corresponds to deletion and this corresponds to insertion. Okay, and what you would like to maintain, I want to like this could be huge, much larger, uh, much larger stream. It could be much larger stream, and all you want to store is whether there is an index which is non-zero and what is its value. This is what you would like to return at the end of it. So how will you do it? This is huge, right? This is huge. The number of, I mean, I don't know. I just know that there are n numbers. Like there are n indexes where I want to do this update operations, but the number of updates could be huge, right? For example, look at your graph. I do edge insert delete. I could do as much time as possible, right? As graphs operation changes, right? But the number of vertices, if I know in advance, they remain the same. So in that sense, this is like it could be huge number of operation, and all I want to know at the end whether there is an index where it is 0, because I could be in the beginning maybe it's all 0, but when I add something I become negative, I add something I become not 0 again, and all kind of things can be possible. How do we maintain this in a small space? What? Of course I can maintain this in n bits. No, I just maintain this a1 to an, right? Whenever something comes, I go to that index and I update it. I can do this, right? I know there are n numbers, so then I maintain this 0 vector in the beginning, initialize it, and whenever whichever coordinate comes, I just go to that particular coordinate and make the corresponding change. If it says add, I add. If it says delete, I delete. And I remain the value. So at any point of time, so roughly a space like, if you talk in terms of words, n words are enough, or n polylog bits are enough. But is that the best we can do? Yeah. Can we do L0 sampling here? Right? So what does L0 sampling will do? Okay, whatever it does, I mean, if you recall correctly, I'm just going to maintain one L0 sample, right? So I think I treat, let's call this vector A, a1, a2, an as vector A of dimension n, right? Now I have this matrix, right, which is A of dimension say log square n times n, and I multiply with this, right? But I told you how to update this last time, right? When insertion comes, what you should do, deletion comes, what you should do, right? And we can maintain this in polylog n, right? What are we storing? Like here, we are going to store one vector of length log square n. This is what we are going to store, this log square n vector multiplication, and we are going to store some a, b, c, some hash functions to maintain this, like a, b, and some prime, some random number, but these are going to take you some order log n bits, right? So in order log square n bit, I can actually return these things to you. Right? So this is where the L0 sampling comes. Now, I would like to maybe know the minimum. I will like to know some other norm, right? How do we go about doing it, right? So, like LP norm of this A0 to AN in polylog n space or something, right? And we can do all those things, but I will postpone that for the time when I do linear algebra, like sketching for linear algebra. But here's a very simple application of L0 sampling, right? I look at this, and so what does it tells you? That something to take home message is, if all I need is an index and its value, L0 sampling is great, okay? If all I need is an index and its value, then L0 sampling works, right? So this is my message one. This is what I would like you to take home, right? Okay, but I also made a claim. I mean, I shouldn't have, like, I didn't made a claim, but I said that actually, so let me write down this lemma which I proved last time. This is a lemma which we proved last time completely in details. So there exists a random matrix. There exists a random matrix A, okay, in R to the power big O of log square n times n. That is a random matrix A in R square log n, such that for any x in R to the power n, okay, with probability at least 1 minus 1 by poly n, 1 by 1 to the power n to the power c, and this c you can just make as much as you wish by taking a constant big enough here, okay, n to the power c, we can learn I xi from ax, right? This is what we proved last time, okay? And we proved it first that there exists a random matrix, and then we proved it that we can implement this using pairwise hash function. Using pairwise hash function, we can implement this efficiently. Implement this in polylog n space, right? This is what we saw. And so basically, I mean, people prove this for this application, and it's only later that people use it for graph purposes and this and this, but this has been around for a long time in this model, okay? Okay, so we will do LP sampling later, but I also said something interesting last time, which was that in fact we can also prove something more here, right? It returns, so let's add a star here, star, what do you call it? It returns I xi with probability 1 over support of x, right? So it's basically uniformly at random over the support, right? but we didn't prove this, and I'm like, the kind of construction which I gave you is not good enough to prove this, but still the construction has like almost 1 over support it will give you. So how did we go about proving it? If you remember, we said you are given a some vector x, let I be the index, let I be the index, so let I be the set of indices of x, set of indices where x has non-zero entry. Okay, and what did we prove? We said, great. Then there exists S in S0, S1, dot 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 S log n, where if you recall, S0 was formed by all being 1, Si was formed by taking probability 1 over 2 to the power I at each entry. This is how it be formed. Then there exists S in this such that I intersection S, a probability that I intersection S is 1 is at least 1 over 8. Right? This is what we proved. Now let's just go back to the proof and let's check what were we saying. Right? So the way the proof went is exactly like this. Probability I intersection sum, and we fix that I is between some 2 to the power I minus 2 and is strictly less than 2 to the power I minus 1. Okay? And what did we say? Oh, great. I intersection Si is 1 is nothing but summation j in I, probability that j is in Si, and for all k in I minus j, k is not in Si. Okay, this is what we proved. All right, we took the sum over this. Okay, now forget about the sum. Let's take one entry. Right? What is the probability that one particular entry is what? So what is the probability if I say, hey, I intersection Si is equal to j? If I say, what is the probability that I intersection S is equal to j, like one particular entry, then this is nothing but one term of this, right? So what is that? So if, then that will be equal to 1 over 2 power I of j being in Si, and every place I am just uniformly at random tossing a coin and putting 0, 1. So what it will be? 1 minus 1 over 2 to the power I mod I minus 1. This is exactly the probability which it is equal to, right? Now let's estimate this probability and let's see where does it fall, like lower and upper bound on this, and then we will know how close to the uniform distribution it is over support or not. Okay, great. So let's, if I have to say less than equal to, then I can write it 1 over 2 power I. So what should I substitute I here? If I want to be less than equal to, this is less than 1, then I should take power which is more, right? If I want an upper bound, right? So I should write here 2 to the power I minus 2 minus 1, okay? Okay. Now this is equal to 1 over 2 to the power I, right? And forget I. Can I forget minus 1? Yeah, it's been. Can I forget minus 1? It's okay. Let's forget minus 1. I mean, like, who cares? But if this is what it is, then this will be what? If you notice, it will be 1 over e power 4. Because this is roughly 1 over e minus 2. So, e square. Right? Because 1 minus 1 by x to the power x is roughly 1 over e. Okay? So, this is what I have used here. Okay? So, it is 1 over e square. Okay? Great. Now, so this is an upper bound. And if I wanted lower bound, then what I would have said, okay, this is greater than equal to 1 over 2 power I, 1 minus 1 by 2 to the power I, right? No, this is, okay, 2 to the power I minus 1, correct? And then it will be roughly equal to, of course minus 1 because, right? So if I forget minus 1, it will become equal to 2 to the power I what it will be? 1 over E? What is this? Wait, there's something wrong here. No. This is not E square, it's E power 4 because it is 2 power I minus 2, right? So 2 power I into divided by 4. This is like divided by 4. So this is 1 by 4 and this will be 1 over E square. Okay. So the probability probability I intersection Si is equal to J is at least 1 over 2 power I times 1 over E square times 1 over 2 power I 1 over E power 4. Okay. Now 2 power I is roughly equal to cardinality of I, right, more or less. So this probability is like, I mean the algorithm which we gave is not completely uniform over the support, but it is almost uniform over its support. Okay, this is what this calculation shows, and this is a useful thing to have. Okay. Okay, good. So all clear from up until now here? Okay. So then like one should just do these simple calculations to check yourself, and if you want exactly 1 over support of X, then it requires a different construction, which we will do much later, not now. I mean, we are not equipped to do. Okay. Okay, so I will write down this. It returns IXI with probability 1 over support of X. Okay, for now let's just assume this. Okay. So the next question which I have, how many of you know how to test whether a graph is a bipartite or not? Do you know how to test whether a graph is a bipartite or not? So this will remain our moral story for next 2-3 lectures. Okay, or this is the key to understanding. Okay, so now graph bipartite. Suppose, and now forget about edge insertion, edge deletion, nothing. Do you know how to test whether graph is bipartite? Okay. How to test whether a graph is bipartite? What is an algorithm we know? So how will you do BFS? Good. Okay.
In the graph, if there is an edge in the same level, so it will give you out cycle. So we have a property, the graph is bipartite if it doesn't contain out cycles.
Fine. So suppose my edges are coming. So this is an algorithm he told me just now, that you maintain a BFS tree. If any point of time you find an edge in any level, then you output, what do you call that? It's not bipartite. Okay. Now my edges are coming E1, E2, EM, and this is just edge insertion, no deletion. And I want to maintain a sketch. Okay. What do I want to like? Maintain a sketch. Forget about space for now. Maintain a sketch so that I can support bipartiteness. I can look at the sketch, and looking at this, with high probability or deterministically, whatever you want to say, we can say, hey, this graph is bipartite. Of course, I can store everything, and then that's great. But then that is going to take m log n space, remember, in terms of bits or m words, whatever you want to say. Okay? So can we try to maintain Haar algorithm in a clever way? Hmm? Yeah, graph is connected for all that. But for a long time, imagine I give you a complete bipartite graph. I give you complete bipartite graph. So if edges are coming, what should I store or not store? I keep maintain a spanning tree. What should I do now? Suppose imagine that all the edges of a spanning tree came first. So I have a spanning tree after n minus 1 edges. Now next what should I do? Yes. It's even. If odd, great. I succeeded. I mean, he can check because he's checking only with respect to this spanning tree. A, time is not an issue, and B, he's just checking in this spanning tree, so easy. Okay, fine. So suppose it participates into even cycle. What should I do now? Should I delete it, forget it, or should I keep it? Do you realize if this would have been okay? Fair enough. Okay, go ahead. Okay. Do you know any other algorithm to test if the graph is bipartite or not? Okay. So let's say I'm going to do graph construction, and it give you a different algorithm to test whether the graph is bipartite or not, and then let's see if we can maintain this. Okay. So this is called double cover of a graph. What? Okay. So if it is not, then what should I do? because it is not a, if it is not a BFS tree, this property wouldn't even hold. It's more non-trivial than just trying to do a little bit of this. Okay, so if you have not seen this, I mean, it is like, okay, I mean, we have used it for several times, this graph for in parameterized complexity. So at least I knew this graph long back. Okay, let's see. But so I'm going to make a definition. For a graph GVE, okay, for a graph GVE, let dg is v prime e prime, okay, v prime e prime, let dg be the graph, nothing is working. Be the graph, okay, constructed as follows. Okay, what do you do when you reduce dominating set from undirected graph to bipartite graph? If I want to show dominating set is W1 hard or NP complete from undirected graph to bipartite graph, what do you do? Constructed as follows. For each V in V, okay, we have two copies. Construct V1, V2 in V prime, and for each edge U comma V in E, what I will do? I will make add U1 V1, no, U1 V2 and V2 U1, what am I writing? V1 U2, okay? Okay, U1 V2, U1 V2 and U2 V1. This doesn't matter. Okay, let's write down just to look nicer to V1. Okay? Add to E prime. Okay? This is the construction I do. Now my question is, looking at graph G and DG, can you say something about bipartiteness? So for example, how will this graph look like? So let's take one example, right? So if it will be, so I will make two copies of this. So I made two copies of this. 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 This guy is to this. So I add this edge and I add this edge, right? And similarly here I will add second copy, and here what will I add? First copy will go to the second guy, right? So this is. I mean, I just on purpose drew this graph. What is the property of this graph and this graph? Do you see something different here? Huh? Look, we will be able to do this just by connectivity. Like I'm not just by connectivity I will be able to do it, because all I have taught you up until now is just how to do big connect. So what is the property between this and this? Do you see something? What is the property? How many connected components are here? This is one connected component. and this is another connected component. Yes. So the lemma will be, this is what we'll prove. Lemma that a graph, let k be the number of connected, let k be the number of connected components in G. Let k be the number of connected components in G, okay? Then D of G has 2k connected components, if and only if G is bipartite. Do you have some red and blue pen? These all are just not.
Green is there.
Green I don't want to use. It's like invisible. It's invisible. Okay, give me red at least. Ask them to get you blue and black. Okay, so for proof, I'm just going to assume that we have just one connected component, then you can apply to each connected component. Okay. So notice one thing first of all, okay. We will only prove when G is connected, okay, and rest proof will just follow. Okay. Now notice if G is bipartite, sorry, if G is not bipartite, if G is not bipartite, implies there exists an odd cycle. C, some CV. Okay, claim. There exists a path from V1 to V2 or vice versa. In fact, both will be there. This is my claim. Right? There exists a path from V1 to V2. Yes. Why? Just start here, right? I mean, you will go, and eventually will, because what is this guy? Right? Eventually, for this edge, you will go to the other side, right? Because look at it's an odd cycle. So first will take you the other side, second edge will take you to this side, and final edge will, like odd edge, always takes you to the other side. So actually the property of this graph is amazing, is that, okay, I mean, let me tell you a bit more. So what does this transformation do? It transforms every odd cycle into a path. So this is why odd cycle transversal becomes a problem about hitting paths in this. And this is also true in directed graph, and we try to utilize this directed graph to show directed odd cycle transversal is FPT, but we didn't manage. But this shows you that you will get a factor 2 approximation using this tricks. Okay, so if G is not bipartite, there exists an odd cycle, there exists a path from V1 to V2 or vice versa. Okay. Now G is connected. Okay. Since G is connected, what is the property? Either U, since G is connected, V is reachable to every vertex. V is reachable to every vertex in V. Right? Since G is connected, V is reachable to every vertex in V. Okay? Implies for all W, okay, for all W, there exists a path from either, for all W, there exists a path from either U1 to W1 or W2 and vice versa. Right? U1 could have a path to any one of them, W1 to W2 or vice versa. Now, what does this imply? Now, look at any two paths. Every path is either reachable to U1 or U2 because the graph is connected, right? And U1, U2 is connected, every path is either reachable to V1 or V2, and so you have two connected components, and because you have an odd cycle, V1 and V2 are reachable. Okay, so this implies that if G is non-bipartite, then you just have only G, D of G has one connected component. And if D of G, now suppose D of G has only one connected component, what happens then? Suppose D of G has only one connected component. What does that imply? There exists a path from U1, there exists some pair, there exists a path between U1 to U2 for some U. Look at this path, right? Now, this path from U1 to U2 corresponds to what? This corresponds to odd cycle. Done. Right? So G can't be bipartite. So we have shown this lemma. Okay. Now that we are enriched with this lemma, can we now design an algorithm for edge insertion? Just for edge insertion? We are just doing edge insertion, we're not even doing edge deletion or something, just for edge insertion. What will we do? Huh? We'll deal with this. But like just for simply, I mean, like what will we do? If there is edge insertion coming, can we maintain a sketch in n polylog in space? That's it. So what will we store? That is like sketch. But if only edge insertion is coming, I can maintain spanning trees, right? So what I want to do, maintain spanning forest for G and D of G. So like I have some edge coming, right? Then when edge UV comes, right? Edge UV comes, what do I check? Is U and V belongs to two different connected components? If yes, then I keep it, otherwise I don't keep it. And for DG, what will I do? I know UV corresponds, it's a local operation. So UV corresponds to what two edges? Well, it corresponds to U1 V2 and U2 V1, right? If any of these edges goes to two different connected components, you keep it, otherwise you delete it. Okay. So how many edges you would have kept here? N minus 1. How many edges you would have kept here? 2n minus 1. Right? Because the number of nodes that we have done is just doubled. Right? So I can maintain all these things in order n log n bits. Right? And I can check whether a graph is bipartite or not. Excellent. Right? Yes, so now, so we don't have to like if you would have been doing dynamic, I would have kept this count business, but it is streaming, so I just keep this. At the end, you will ask me, so I just check the connected component here, check the number of connected components here. If they are double, then it is bipartite. If it is not double, it is not bipartite, and it is deterministic. Okay, okay. But now let's allow that. Dynamic edge stream. Okay. Then what will we do if I do dynamic edge stream? if I do dynamic edge string, what should I do? Right? I just need to maintain these two things dynamically, right? So for every vertex here, I will keep a sketch, like log n sketches for each of L0 sampling sketch, right? So what are we going to keep? For every vertex here, for every vertex V1, we are going to have sketches like A1 tilde, A2 tilde, dot dot dot, AN tilde, sorry, A log n tilde, similarly, or yeah, log n of them for every V1, V2, Vn, and here V1 and like 2, both copies, you maintain sketches, right? So this we can do it in n polylog n, right? Because the way we did connectivity, and I can just check the number of connected components again, and we can maintain this, and we know how to dynamically do this. Okay. Last time someone asked me this question, that why for the first one we keep matrix A1, for the second one we keep matrix A2, and it is random. It is random because look at the vector. What does it says you? For any x in Rn with probability, I did not. So A1 gave you some set of connected components. A1 gave you some set of connected components, right? If I apply A1 on the summation of this vector, A1 is not a random for this. But when you apply A2 on some Z, so basically what it tells you that, look, if you give me any x in R to the power n and you choose some matrix randomly, then that's good. So almost every matrix is good for it. This is what it means by 1 minus 1 by nc probability will succeed, right? So here what did I do? We said, okay, fine, let's look at x1 tilde, x2 tilde, x3 tilde, x4 tilde, x5 tilde, right? We added this up, but I did not use A2 to construct this connected component. So with respect to, for this vector, A2 is random. Because if I would have used A2, I would have got some different connected component for all that I know. Okay, anyway. So it is important that if you choose a vector, then the matrix what you choose is random with respect to that vector. Okay, so this was about that we know now how to do bipartiteness from linear sketching. Okay, now let's do, if I want to do, say for example, approximate minimum spanning tree. Okay, so now what we are going to do is approximate MST. MST. So what are we given? We are given graph G and function from edge of G to some R positive, say that it could have negative weight also, doesn't matter. Okay, edge bit, positive edge bits, and we have to find a spanning tree with minimum weight. Okay, now I give you a approximate additional parameter meter epsilon. You need to output 1 plus epsilon approximation to minimum weight spanning tree. Can be reduced to connectivity, because that's all that we have learned. And you also assume that the weights are bounded, like otherwise, I mean, it becomes very difficult. Okay, so you are assuming that max weight is like is at most Boolean. Okay. Yeah. So weights. So W is in 1 to W. W is in Boolean. This is okay. Just to make our life easier, let's assume that G is connected. Otherwise, we can apply to also get minimum weight spanning forest. So G is connected. I mean, anyway, if the graph was not connected, I could just first run my n. I mean, I could just maintain two different things to just check whether connected or not. I could have done that. Okay. So assume G is connected. So what will you do? First, let's assume that the graph had just weight 1 and 2, just for okay. So suppose I told you, let's look at G1 and G2. Okay, it's a subgraph of G, okay, where each edge has weight 1, and G2 subgraph of G where each weight is exactly 2, right? If I told you this, I told you G1, G2, what information you need to ask from me, that if I give you that information, then you can tell me what is the minimum weights, what is the weight of the minimum weight spanning tree. Do you get my question? I told you G1, G2. I'm asking you, ask me a question about G1, right? Of course, you don't ask me minimum weight spanning tree or something. But if you ask me some query which we know how to model, if I told you those two numbers, okay, you will tell me exactly equal to exactly the minimum weight spanning tree. That's it, right? So if I give you the number of connected components in G1, and if I give you the number of connected components in G2, then you will be done. Because let's apply Kruskal's or Prim. What will it do? It always tries to put minimum weight edges first, right? Right? This is what. So like it sorts the edges. Is it Prim or Kruskal? Kruskal, right? And then it will first form number of connected components is 1, and then fill it with the number of connected components in 2. Do you agree to that? So that's it. So all we need is an information about number of connected components in G1 and G2. Because then, right, it is connected, right? So if I told you how many connected components are here, that's enough, right? So if I told you, say, N1 is the number of connected components of G1, then we know what is the minimum weight spanning tree looks. What is the weight of minimum weight spanning tree? Don't we? Right? We know this is equal to N1 plus 2 times N minus 1. No, 2 times N minus N1. N minus 1 minus N1. Because total number of edges is like N minus 1. You have used N1 edges with weight 1, and the remaining edges you will use with weight 2. So what is the weight of this exactly equal to? N1 is the number of connected components of G1. Wait. I'm being stupid. Look, no, wait. So if n1 is the number of connected components of G, then we need n1 minus 1 edges of weight 2 to connect them up. Right? So then the minimum weight spanning tree will be 2 times n1 minus 1, this is the number of edges of weight 2, which we have added, plus n minus n1. Do we need minus 1 also?
No, minus the number of connected. No, that's n1. Yeah, so n minus n1. Correct.
So this will be equal to, if I do correctly everything, then it should equal to 2 minus n2 minus 2. No, plus 2 times n1 minus n1, so this should be just n1 plus n1 minus n2, right? So knowing a connected component could just help, okay? Good. So we'll apply such tricks here. So let's generalize it, okay? And let's generalize it, and this is a trick by Bernard Schlegel, which has been which you can use it for various purposes. So what you do is the following. Let's try to generalize this lemma from one with just 2 numbers to having, say, several numbers, and how we could do this, okay? So what I'm going to prove to you, okay. So what we do is that for each edge E, okay, round weight of E to 1 plus epsilon to the power I, okay. This is what I round up to, 1 plus epsilon to the power I. I is some like power, right? Epsilon is some non-zero number, and it is like poly n. So like roughly I will be up to 0 to polylog, 0 to order log n, right? So I look at the weight, I say, hey, what is the closest, right? So round V to closest 1 plus I epsilon to the power I. Now how many weights do we have in the graph? If you notice now, since I assume the weight is at most poly n, the weights are like 1 plus epsilon, 1 plus epsilon square, dot, 1 plus epsilon, some order log n. This is what. So number of weights will be like distinct order log n weights. Okay. Now, but we need a lemma which will exactly tell us what we need from, like, which should tell us that, okay, number of connected component here, number of connected component here. If I know, then I will be able to tell you like what is exactly precisely the minimum weight spanning tree, like close to 1 plus epsilon. Am I right? So let's prove following lemma. Okay, these are all just static things. There's nothing fancy happening here. But the point is, if we can reduce our problem to counting number of connected components, then we know how to do it using sketches. That's it. Let T be a minimum weight spanning tree of G. Okay, and set R equal to log 1 plus epsilon into W, because that is what it can go. Okay, then weight of T is less than equal to, any guess, n minus 1 plus n minus 1 plus epsilon to the power R. Okay, and we have to also add some more things, plus summation I equal to 0 to R. Okay, I'll tell you what lambda is are. Connected component of Gi. Okay, and then we will show this is less than equal to 1 plus epsilon times weight of T. Here lambda I is equal to 1 plus epsilon to the power I. This is what it is. No, what I'm doing. 1 plus epsilon I plus 1 minus 1 plus epsilon to the power I. Okay. So, given a graph G prime, G, we have constructed G prime where edge weights are rounded up, right? Okay. So, G prime has been constructed from G by rounding weights in G. So, clearly minimum weight spanning tree can only grow, right? I mean, right? So, definitely weight of T, where T is a minimum weight spanning tree, is less than equal to weight of T prime, where T is minimum weight spanning tree of G and T prime is minimum weight spanning tree of G prime. It is definitely less than equal to this, because you take any set of edges which forms this, if you forget the edge weights, you will, I mean, you have only increased the edge weights. So, all I need to show that, if I need to show that this is less than equal to 1 plus epsilon times weight of T, and then we will be done. Okay. Okay, so how do we do weight of T? So we'll do this Kruskal's algorithm, right? So first, how many edges of weight 1 plus epsilon will the Kruskal algorithm will add? Here when we were doing, how many edges did it add? N minus the connected component of G1. That is exactly how much it adds, the weights of this, right? Okay. Okay. So Kruskal will add first N minus connected component of G number of edges of weight 1 plus epsilon, right? Because we do not have any edge with weight 1, we have everything with weight 1 plus epsilon. How many weight? We can also actually, we could have also done up to like start from 0 actually, okay? I is from 0 to this, because it is R positive, right? Yeah, so it's better. Otherwise, we will be so it will be like half weight 1, because I'm only saying R positive, right? I'm not saying negative. So I could also have half, 1/3, 1/4, right? So you just turn it to 1. How many weights of 1 plus epsilon will you add? This much you will add, because look at the connected component on G2. I claim you will add these many edges of weight 1 plus epsilon. Look, you can only add number of connected component number after G1. How many edges can you add anyway? Number of connected component minus 1 for all that you care, right? Out of which, how many G2 will take? This much it will take. This is all that it is, right? So after the first operation, you like when you told me 1 and 2, what did you say? You say, hey, look, how many edges weight of 2 will there? It is just proportional to the number of connected component of G1, because you can contract this now. How many vertices you have? as many as number of connected component of G1, and you are going to make that connected by adding edges from G2. Right? So that is proportional to the number of edges, number of connected component in G1. Okay? Okay. So what is weight of T prime? Weight of T prime is equal to so after first operation, how many connected components are after first operation? How many connected components of my spanning tree at that point of time will be? Right. So the number of more edges to be added is only across them, right? So the number of edges which I can add is at most connected components of G1 minus 1, right? Out of which I'm asking how many of them will be taken by connected component of G2. Imagine yourself that now what is the meaning of the connected component of G1 minus connected component of G2, right? So what is the connected component of G2? Right? Look at a connected component of G2. Now, if I look at a connected component of G2, either it is completely contained inside this or it is going to patch it up. But can it patch it up? What is that called? Notice, what are these guys? What are these connected components? It's only on edges of weight 2, right? Now, how many connected components here will we have from G2 which will be going across, right? Because that is the only thing which you will add from G2, right? So imagine yourself that now if I contract each of these guys, how many edges do I have? If I contract each of them, how many edges do I have? Contract each connected component, right? How many edges do I have going across? These are connected component of G2, right? So each of these guys can contribute. So now when I look at a connected component here, where can I have an edge here? Like this or like this? Huh? Here. Yes. So we will, but how many such edges will be adding here? Okay. So let's look at this other way around. Okay. Let alpha I did I use alpha? Okay, be the, forget for now. Let alpha I be the, so this is my minimum weight spanning tree, and suppose I have some 1 to w weights, okay? And let alpha I be the number of edges in T, and this is T, the minimum weight spanning tree, with the number of edges in T of weight I. Okay? Then what is the weight of MST? So weight of MST will be summation I going from 1 to W alpha I. Okay? And notice that these alpha i's are independent of what minimum weight spanning tree do you pick. They do not depend on the minimum weight spanning tree. They are independent of how many number of edges will you get of same weight is actually, it is invariant under any minimum weight spanning tree. I mean, you can prove this yourself, but this is true. Okay. Also observe, let's observe this following quantity. Let's see if this is correct. Let's observe for all L between 0 to W minus 1, and W is integer, for example, okay? For all, I want to say that summation I greater than L, summation I greater than L, and alpha I, okay, is equal to so what I am going to say, you will see what it means. What is C of L? Is C of L is a number of connected components in graph G L where edges have weight at most L, okay? Not exactly equal to L, but at most L, okay? So by assumption, what will be CW? If my graph is connected, then CW is equal to 1, because there is only 1, because I am taking all the edges, okay? Okay. And then what is this equal to? I greater than equal to L, I am going to claim to you that this is going to be equal to CL minus 1. What is CL? All the edges, all the connected components up until edge L minus 1, and how many number of guys can you go up? Look, I am just generalizing whatever I wrote here, right? If I have number of connected components, just 2 weights, then what did we say? How many number of connected, how many extra edges you are going to add beyond that? Is n minus the connected, n minus 1 minus connected component minus 1, sorry, connected component minus 1. This is what you said. So now I am saying, look at all the edges whose weight is more than L. So what is C of L? Is a number of connected components in the graph where all the edges has weight at most L. So how many more edges I will add? CL minus 1. This is clear? Okay. Because G is connected, and now like this is. So now if weight of Ti is this, okay, I want to write this summation. Okay, this is why I have to look at my computation morning. So just 1 second. I did some computation. I equal to 0 to W minus 1. I'm just going to use this inequality. I should not have eaten it up. Summation I going from 0 to W minus I. L equal to 0 to W, I equal to L plus 1 to W, L plus 1 to W alpha I. Okay, I want to write it like this. Okay, so what is this? alpha I is a number of connected components times I, right? So how many times he is going to contribute? I times. In this sum, how many times he is going to contribute? Here, it's like, what is this? Look, think of this way. I wrote I equal to 1 to W alpha I times I, right? So first one is like alpha 1, right? Second one is alpha 2, alpha 2. What is third one? Is alpha 3, alpha 3, alpha 3, so on and so forth. Now you just count like this, right? What is this counting? It is counting like this. Now I am counting like this, counting like this, counting like this. This is exactly what it is, right? So this is row sum and this is just the column sum, right? So this is exactly equal to the same. Okay, at least this is how I look at it, right? So like this is what, so now if I count from here, so summation L equal to 0 to W minus 1, I going from 1 to W alpha I is like 1, 2, 3, next it will be 1, then you will count here L plus 1, so alpha 2 blah blah blah, third and so on and so forth. So this is what this counting is. But what is that? What is that equal to? What is this? Exactly. So this is exactly CL minus 1, right? So this is equal to minus W, because from everyone minus 1 will come, right? And you will get summation, what will we get? L equal to 0 to W minus 1 CL. L equal to 0 to W minus 1 CL. Agree? This is what it is. I equal to 0 to W minus 1 CL. Right? This I substituted with CL minus 1, right? This is what I substituted, right? Which is same as I going from blah. So this is what you will get. So what does it tells us? Now if you look at this formula, isn't it clear what much more do we need to add at every point of time? Whatever I was writing, you will add these many edges of weight 1 plus epsilon. What you don't get? Total is n minus 1, right? In the second step, how many edges will I add?
Here is the connected component which contains all the edges.
Yes, and I know how many of them belongs to C1. Okay, even if you take this, it is perfectly fine. I mean, one can also just maintain this. It is not a very big deal, right? So what can I do? When my edges are coming, right? When my edges are coming, I maintain a spanning tree of each GI, and I claim to you, if you look at the union of these two edges, that gives you a connected component of these two guys. Because whatever the connectivity property of two edges are, that is taken care of the connected components of the second guy. No, I just look at weight 2. But I know my connected component of 1 and 2, I have edges which gives me. But if I take the combination of these two, it will give me a connected component of both. I'm saying, look at a spanning forest of edges with 1, look at the spanning forest of edges with weight 2, and look at the union of this spanning forest. It will give you a connected component of edges on both weight 1 and 2. Look at any other edge. How can it give you a different connected component? Look, what did I say to you? Look at the edges, look at a spanning forest of edges on weight 1 and look at this connected component of F1 and F2, edges of 1 and 2. By claiming that you are not going to get any more spanning edge. So look at that edge. Either it has weight 1. If it has a weight 1, then it is part of some connected component inside. So that is not going to add connected component here because I have taken the union of these edges. If I look at weight 2 edges, right, it is part of completely contained inside some connected component here. So maybe they have merged. So they can only be, I can make bigger connected component. I cannot get smaller connected component. That's it. Okay. So, but why does, now look at this, okay. So now but how do we show that this is equal to 1 plus epsilon time this? So this will just follow from here. This will just follow from here that what is alpha I? It be the number of edges in T of weight I, right? Right. So now look at weight of T prime, right? Weight of T prime is summation. Forget about this. I mean, if you find that a bit confusing, I mean, it's okay. Now look at weight of T prime. I know weight of T prime is equal to this, okay? So it's going to be I equal to 1 to W alpha I, right? Now I is fixed, right? I is basically summation of I is going to be n minus 1. But what is alpha I? Be the, now, okay, but what is this I? So for us, I is like, think of this, I can write it down, summation I equal to 1 to W. What is this? It is 1 plus epsilon, right? Right? So what is the property of alpha I? Alpha I is a, no, alpha I remains alpha I. What is the property of I? What is I? Is basically for us number of edges of weight I. So let's call that 1 plus epsilon to the power I plus 1. So maybe I should write not, yeah. So we have weight of 1. How many edges of weights? 1, right? I minus 1. Right? But what is the property of each I? I is at least 1 plus epsilon I minus 2, right? So I can take out common, right? I can multiply everything. This is less than equal to 1 plus epsilon summation I equal to 1 to W alpha I times I, right? I can write this, which is nothing but minimum weight spanning tree. Because what is the property of I? I mean, this is an overuse of I should not use, let's say J alpha J equal to 1 to W alpha J 1 plus epsilon J minus 1. right? This is what it is. Now what is the property of J? J is between some 1 plus epsilon J minus 2, 1 plus epsilon J minus 1. So this is one. And now if this is given to me, then I can maintain my approximation. How? So what will I do? When edges are coming, I try to maintain a spanning forest for each weight. Okay? For each weight, I will try to maintain a spanning forest. So notice now I will have how many sketches? For every vertex 1 to n, I will have different sketches for different weights because I don't know how many connected component each will give. Look, it's a spanning forest, right? So you will have same vertex v1, v2, vn, v1, v2, vn, and how many of them? As many as r of them, right? So now whenever edge comes, I know what is its weight, right? I can just take its power and I put it in appropriate data structure, right? I put it in appropriate data structure, remove, delete, whatever it comes, I can do this. At the end, now I need to find I know that it stores, all I need to find out now is number of connected components in each of these guys. And if I know the number of connected components in each of these guys, I can get this. So what? So first I find a connected component here. Second, I find connected component of these two guys. Then I find connected component of this and this. Then I find connected component of this and this. And then I can apply this to get the weight. Right? Because it is this plus I equal to this summation C power C. Right? So I can just use this formula itself to. So, and I have. So I find F1 here, spanning forest. F2 here, FR here. Right? So first I will find F1, connected component of F1. Then I find connected component of F1 union F2. Then I find connected component of F1 union F2 union F3. Dot dot dot, connected component of F1 union dot 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 union FR. Right? I can find this. And this is precisely what I have. Where did I? Here, right? And then I subtract this number. So whatever the number I have got, I'll say, hey, this is the weight of the minimum weight spanning tree. And I know because of this formula that this is 1 plus epsilon times this. Okay. Now, how much it's like, this is like, it will also have some 1 over epsilon term here, but it is basically n plus poly log n 1 over epsilon. Okay. Try to prove this lemma. It is, I mean, I got confused. I confused myself, but so I moved to this. But I first proved this, and there's a simple translation from here to here. Like it's really a simple translation once you prove this. Okay, to from here to here. Okay. So after lunch, we will see exact minimum spanning tree and sparsification.